Welcome to Module 5 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification's Bodies of Knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description for free. In this module, we will begin discussing the basic concepts of Six Sigma. This module will take approximately 80 minutes to complete. At the end of this module, there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a Pareto chart template, a Voice of the Customer matrix template, and a rolled throughput yield calculator, all of which are Excel files. The statistical measure used by teams to understand variation in a process is known as standard deviation. Standard deviation is represented in math by the lowercase Greek letter sigma. In this section, we will dive deeper into one of the most important metrics used in Six Sigma, standard deviation, which measures the distance between data points and the mean of all data. A large standard deviation means an overall wide spread of points. A smaller standard deviation means a closely clustered set of points. There are two ways to calculate this metric, and we will show you how to calculate this metric regardless of whether the data is from an entire population or simply just a sample of that population. Standard deviation gives you an idea on how much variation exists within a process. It is used to measure the dispersion of the dataset relative to its mean. The way we calculate the standard deviation when dealing with population data is different from calculating it when dealing with sample of the population. That is because the population data includes all of the data for a given class. It is the entire population of possible data points. As a result, the calculated deviation is more accurate. Here we see the formula that is used for calculating standard deviation when we are dealing with the entire population of data points. In Six Sigma calculations, the lowercase sigma is generally used to represent the standard deviation. The lowercase mu is used to represent the mean of population data. Whenever we see the uppercase sigma in a formula, the E-looking Greek character, it means that you need to add up all the results of the calculations done for the items listed in parentheses. You will see the uppercase N above the sigma, which reminds you that you are repeating the calculations for each data element you are using to calculate the standard deviation, and each of those individual data elements are represented by the X. We start by calculating the mean for the population data. This is represented by the Greek letter mu. When we say the mean, what we are actually saying is that we need to calculate the average of all the data points. If we remember back in grade school, the term we use to declare that we are adding numbers is the word sum. So to calculate the average, we need to obtain the sum of the value of all the data points. We need to add all of the values together. Then we need to count the total number of elements contained within our data set. This is not the value, but simply a count to determine how many data points we have. In order to obtain the average, to get the mean of the population data, we divide the sum of the value of all the data points by the number of data points we counted. So if our population data is composed of 10,000 individual data points, we add the values of all these individual data points together. Then we divide that total value with the count of the total data points, or in that example, 10,000. Next, we need to take the value of each individual data point in the data set, which is represented by the X, and subtract the mean, the average value for the entire data set, and then square it. To square, we simply multiply the value by itself, and we do this for each individual value in the data set. So if our population data consists of 10,000 individual data points, we need to subtract the mean. then average all of those data points from each individual data point, and then square the value so that we have a second value to represent those 10,000 data points. As you can see, dealing with population data can be a daunting task because there can be a lot of individual data points. In processes where data is captured automatically, there could be millions of data points, which makes working with population data harder, more time consuming, and more expensive than working with a simple sample. Remember that our uppercase sigma, that little e letter, tells us to repeat the calculation for each of the data points. Well, now that we have a second set of values for each of those data points, because the rest of the formula under the square root sign simply tells you to add up all the numbers you just calculated and divide by n, where n is the number of items in your data set. Or to put it another way, you need to find the mean of the second set of values that we just calculated. This new average represents the variance of our data set. In order to find the standard deviation, we must have a variance between each of the individual data points. In the last step, we take the variance we just calculated and we find its square root. So the standard deviation of the population data set is the square root of the variance. And although it is represented by the lowercase Greek letter sigma, this number is not the same as the sigma level, which can be quite confusing. Rather, the variance is the amount of variation that exists between each of the individual data points within a given data set. While statistics based on total population data are always more accurate than those based on sample data, you will probably work from sample data more often. It just becomes too expensive or even impossible to get population data for many elements. Sometimes the data is measuring events or states over time, which means population data doesn't exist. For example, if you want to understand temperature fluctuations in a warehouse, you might record the temperature at a certain location every 10 minutes. After several days, you have sufficient sample data to analyze. In an office environment, you may randomly sample the reasons for denied medical claims. Or a park ranger may take measurements for river height 3 times per day for a month. The key is that a sample must be random and unbiased so that it properly represents the population data. Any form of bias can skew the resulting data points, making them useless in a Six Sigma initiative. So, here we see the formula that is used for calculating standard deviation when we are dealing with only a sample of the entire population of data points. It looks very similar to the last formula. Some of the letters are different, but the noticeable difference is that n minus 1. Since we are not dealing with the entire population, we cannot use the lowercase Greek letter sigma, so we need to use the letter s to represent the standard deviation. And since we are not dealing with the entire population, we cannot use mu, so we have to use an x bar to represent the mean of the sample data. Just like in the last formula, whenever we see the uppercase sigma in the formula, the E-looking Greek character, it means that you need to add up all the results of the calculations done before the item listed in parentheses. You will see the uppercase N above sigma, which reminds you that you are repeating the calculation for each data element that you are using to calculate the standard deviation. And each of those individual data elements are represented by X. The only difference between calculating the standard deviation for the population data and calculating it for a sample of the population data is the final step of the equation. Remember, in the previous example, we had to create a second set of values for each data set by first finding the average for the entire data set, then subtracting that average from each individual data point within the data set, and then squaring it, multiplying it by itself, and then eventually finding the average for this second set of values in order to find the variance. Well, when dealing with the sample of the population data, instead of dividing the sum of the second set of values by the number of data points, we need to divide it by one less than the total number of data points. So, if we had a data set composed of 10,000 values to find the variance, we would divide by 9,999 instead of 10,000. This makes up for the inaccuracies of the population data. Admittedly, if you are calculating standard deviation by hand, it can be a lot of arithmetic. Luckily, once the statistical concepts behind the numbers are understood, statistical analysis software such as Excel and Minitab can be used to accurately crunch numbers. Standard deviation is automatically calculated in most statistical analysis software programs by clicking a button after you enter the data set. The standard deviation is also calculated automatically by such software programs when you initiate other calculations that require standard deviation. When using Excel, however, to calculate the standard deviation, it is important to remember that we can only calculate it for sample populations. We start by either entering or pasting the data into a single column. We could follow the previous steps and manually calculate the standard deviation, especially if we are working with an entire population and not just the sample of the population. In which case, we would have to create a second column with the average of data set repeated on every row, a third column that subtracts the average in the second column from the individual values in the first column, a fourth column which calculates the square for each value in the third column, then a single cell in the fifth column that calculates the average of all the values in the fourth column, and a second cell in the fifth column that finds the square root of the first cell. But that is a lot of steps when all you need to do is enter equals STDEV, open and close parentheses, then select all of the cells of data that you want to calculate the standard deviation for, and click enter, then voila. In that cell, the moment you clicked enter, Excel automatically calculated the standard deviation for the entire dataset you selected. But as stated previously, this only calculates the standard deviation for a sample of the population data. The formula in Excel uses the n-1 math, which means you can use this formula for samples and not for populations. So, if you are working with an entire population, then you will need to either use Minitab or manually calculate the standard deviation using the steps we discussed previously, with each step being completed in a new column, since most of the calculations are specific to each individual data point up until the averaging of the second set of values. The Pareto Principle says that 20% of the causes lead up to 80% of the effects. It is the law of the vital few, which states that the vital few inputs drive the majority of the outputs. In this section, we will take a closer look at the Pareto Principle and the Pareto Chart, which is an important tool in the Six Sigma Toolkit. We will show you how to create a basic Pareto chart using Excel, and even how to use them during the course of a Six Sigma project. The Pareto Principle, also called the 80-20 rule, says that 20% of the causes lead to 80% of the effects. The Pareto Principle was first suggested by management consultant Joseph Giron and was named after Vilfredo Pareto, an economist in Italy who had once written that 20% of the nation's people owned 80% of its land. Today, the concept is commonplace with business professionals stating that 80% of the sales come from 20% of the customers, and volunteer organizations operating with 20% of the people who do 80% of the work. The principle is critical to Six Sigma, not because cause and effects line up nicely via the 80-20 breakdown, but because it almost universally applies that a few inputs create more impact than all of the other inputs. Individuals seeking to reduce defects can identify the major inputs that will create the greatest impact on the outcome. The Pareto chart allows project teams to determine where improvements will make the biggest impact to the bottom line. The Pareto principle is best displayed using a Pareto chart, which is a graphical representation of data elements, usually inputs or causes, in a ranked bar or column chart. Unlike a regular column chart, the bars in a Pareto chart are arranged by the order of their height, with the highest on the left and the lowest on the right. Most charts will also feature a line that indicates the total percentage, starting lower on the left until it reaches 100% on the right. Statistical software can be used to create such charts with formatting and other elements automatically. But you can also create a basic Pareto chart with a line using just Excel. Even if you don't have statistical software, you can still create a basic Pareto chart in Excel. Of course, it may take an extra few steps to create it than it would using a program like Minitab, but at $1,600, most people cannot afford to purchase their own copy of Minitab. To create a Pareto chart in Excel, we start by creating a column for the data labels. Pareto charts work well when you have quantifiable causes for a defect or other effect. No matter what type of data you are using, enter it in order from largest to smallest for Pareto chart purposes. Next, we create a column for the count where we enter the total for each cause. Then we create a third column for the cumulative count, which provides a running total. Finally, you create a fourth column for percentage. You do this by dividing the individual count for the row in the second column by the total count of all the rows in the second column. Now that we have a table consisting of 4 columns, we need to first make sure that the data is listed in order from largest to smallest, with the largest in the first row and the smallest in the last row. Then we can highlight the reason or defect, which was our first column, and the percentages column, which was the last column we created. These will be the data points used by Excel in order to create the Pareto chart. With those columns highlighted, we need to choose the Insert tab from the top ribbon in Excel and locate the Charts section. There you will see several options like column charts, bar charts, pie charts, and more. Make sure that you choose the chart that has the vertical bars or columns. This is an automated process that uses your default format and settings. But this will only create the chart automatically, as the trend line will need to be added manually to the chart. We accomplish this by selecting the Add Chart element from the Format tab and select Trend Line. You will have several options to choose from, and each will create a different look to the chart. But in creating a Pareto chart, it is recommended that you use either exponential or linear trendline design. Data labels are only slightly important. After all, we are trying to decide which root causes have the greatest impact. So, to do this, while you still have the chart selected and can see the Chart Format tab, we need to select Add Chart Element again, and this time choose Data Labels. There are several options to choose from, but make sure that the labels are legible. It is recommended that you choose either the option for outside end or outside base, as this will put the labels outside of the chart rather than inside them. Pareto charts are helpful analytical tools when you need to analyze frequencies or causes of problems. They also help narrow an approach for a problem that has many causes or is too broad to address in a single improvement project. Like the claims denial example that we discussed in the book, you can find a single cause to work on that can yield large results across the entire process. Pareto charts are also helpful when communicating information about causes to others, especially those outside of the Six Sigma process. Although Pareto charts are a powerful analytical tool, they also represent complex data in a visual format that is familiar to most anyone. Business professionals know how to read a bar chart, and putting the chart in order only makes it easier for individuals to see the true causes behind some issues. For this reason, many Six Sigma experts regularly include Pareto charts when presenting to business leaders and others, especially if the data might be considered surprising or needs visual reinforcement. The voice of the customer, or VOC, is a foundational concept in many quality programs that use feedback from the customer in order to improve the quality of a product or service. In this section, we are going to discuss the concept of the voice of the customer. We will talk about the different methods of capture, how a voice of the customer campaign is built, and the different types of feedback we need. We will also go into greater detail on how to select the right tools for the job and what a Likert scale is. Successful voice of the customer programs are proactive and constant in their desire for feedback, and technology makes it possible to seek customer feedback in numerous ways. The voice of the customer can be sought as a means to clarify needs and desires, clarify specific problems with a process, or as a regular part of improvement, customer service, and marketing agendas. There are many different methods used to capture this data. Surveys are very popular and they can be conducted by phone, snail mail, email, or even online. Focus groups are not as common, but we hear about them all the time, especially with more expensive products like cars. Then there are interviews, feedback, and complaint forms, social media or forum interactions, as well as beta and user testing programs. All of these methods have their own unique pros and cons associated with them. Asking the right questions in the right way helps you to create a powerful voice of the customer campaign that provides usable data for Six Sigma teams. Generally, voice of the customer campaigns fall in two types. They can either be general or they can be specific. General feedback is used as a smoke alarm. These campaigns help to gauge customer feelings regarding a product or service and to determine the critical quality elements of that product or service. Specific feedback, on the other hand, helps narrow down issues discovered with a product or service and requires clarifying questions in order to get that information. So let us talk about these two types of campaigns a little bit deeper. General customer feedback is often obtained through feedback forms, customer complaint records, and passive information gathering via websites or social media. Through such methods, organizations are usually testing general waters to get a temperature reading. Are customers happy overall? Dissatisfied overall? And is there any direction as to the cause of the customer feelings? Pick up a feedback form in any fast food restaurant or access the online survey, usually linked to a receipt that you get when you purchase something from a store, and you'll get a good idea of the type of information sought in a general voice of the customer campaign. They ask questions regarding locations, dates, and times, then ask questions such as your overall satisfaction with the company, your interaction with its employees, the prices, products, or service selection, and more. These questions are designed to gauge the general customer feelings on critical quality elements for the store. Understanding your critical to quality factors, or CTQs, is important to designing a strong voice of the customer campaign. Sometimes, organizations want feedback that is specific to a problem, product, or idea. The same tools used in general feedback campaigns can also be used in specific feedback campaigns, but you can also tailor the voice of the customer tool to the need. If you want feedback about a new app, you could use a beta test. If you want to test a product, idea, or marketing campaign, an in-person or online focus group might be best. For specific feedback, you have to ask specific questions. This is especially true if you are seeking additional information or clarification for general feedback. For example, if a company saw a problem with ratings on cleanliness, it might want to know more information about how and where customers note uncleanliness. Without additional feedback, managers might have staff mopping the floors more when customers really felt the store was dirty because of a lack of lighting or because shelves were stocked in a sloppy manner. Getting the right type of feedback and keeping costs and timelines within budget requires selecting the right VOC tool for your product. Some of the more common forms of voice of the customer tools include feedback forms, surveys, use of social media, the conduction of focus groups, and of course, beta testing, especially when the product is a digital one like a new game. Because each of these has their own specific pros and cons, we will discuss them in greater detail. In the Council for Six Sigma Certification Handbook, which you can download in the course description section, there is a table showcasing these tools. The cost of using feedback forms is very low. It is good for gathering lots of data from many different sources without costing a lot of money. It can also be geared towards numerical data so that conducting an analysis of the data will be easier. Unfortunately, one of the biggest drawbacks is that the individual must choose to leave the feedback, and this alone can skew the results in favor of those who feel strongly in one way or the other. The cost of conducting a survey by phone is very high, whereas the cost of conducting it through the mail or online can be drastically reduced. When using the phone or through mail, customers can be randomly selected so the data can be used to draw conclusions about the entire population. The downside is that phone surveys take a lot of time to complete, and many customers will be annoyed by the unwanted calls. Of course, surveys by mail also have their own downside because the customer has to send it back for it to count. And because so many people don't want to complete the survey and send it back, you need to send out more in order to obtain a proper sampling of the entire population. The cost of running a social media campaign is low. In fact, it is possibly the cheapest option for a voice of the customer campaign. Not only does it allow you to seek feedback on a continuous basis, but you can also obtain specific feedback by asking questions on the fly. But it does actually require a social media following, and that means it relies on those followers who already have a favorable view of your products or services. The cost of conducting a focus group depends on whether it is in person or online. In person focus groups tend to be some of the most expensive voice of the customer campaigns to conduct, which is why you only hear about them when it comes to expensive products like cars. While they both allow the moderator to ask in depth questions on the fly, when they are held online, there is no traveling involved, which means there will be a greater chance of participation. Unfortunately, you cannot use this data collected from a focus group in order to make assumptions about the general population because the members of the group are not exactly a random sampling of the population. The cost of beta testing is high because the amount of time it takes to complete and the fact that you need experienced users or testers. Many times, you may even have to pay them to participate. They are great for obtaining specific feedback about a product, service, or process, but it is the lengthiest voice of the customer campaign that one can conduct, sometimes taking only weeks, while other times taking several months in order to complete. When designing your own voice of the customer tool, keep in mind how you intend to use the information gained. If you want to input data into statistical analysis software to test hypotheses or to create visual charts, then you need to ask questions that yield actual data points that can be analyzed using statistics. A popular way to do this is with the Likert Scale. Using a Likert Scale, you would frame all questions so they are answered via a 5-point ranking, such as strongly agree, agree, neutral, disagree, or strongly disagree. The answers are coded with numbers when the data is entered into statistical software. For example, an answer of strongly agree might be coded as 10, agree might be 7, neutral 5, disagree 3, and strongly disagree 1. By using numerical data, you can easily create charts and graphs and run more in-depth statistical analysis. Metrics are extremely important when applying Six Sigma to processes and improvements, requiring that anyone working in a Six Sigma environment to be familiar with them. In this section, we will discuss the basic metrics used in Six Sigma. We will talk about one of the first metrics you will need, defects per million opportunities, and also cover the differences between first-time yield and rolled throughput yield, as well as how to calculate these metrics. Now, we have talked about defects per million opportunities on a number of occasions. To maintain a Six Sigma level, we cannot exceed 3.4 defects per million opportunities. At 5 Sigma level, that increases to 233, then to 6,210 at a 4 Sigma level. The increased number of defects compared to the decrease in Sigma level is exponential. We calculate this metric by simply dividing the number of defects observed by the number of opportunities sampled and then times that by a million. So, if you had 900 opportunities for an error to occur, but that error occurred only twice, then you would divide 2 by 900 and multiply by a million to give you 2,222 defects per million opportunities, which would translate to a 4 sigma level. We have also talked about defects per unit. The defects per unit is a measure of how many defects there are in relation to the number of units tested. The defects per unit is concerned with total defects, and one unit could have more than one defect. We calculate this metric by dividing the total number of defects found in a sample by the number of individual units in that sample. So, if we sampled 50 books from a run of 1,000 and found 3 of them were missing pages, 1 was missing pages and had a torn cover, 2 of them had loose spines, and 1 had an incorrect printing and printing alignment, then we would have a total of 9 errors. 2 of them had multiple defects. We would divide the 9 errors by the 50 books sampled to give an average of 0.18 defects per book. First-time yield is the ratio of units produced to the units of attempted to produce. To calculate the first-time yield, we divide the number of good products produced by the total number of products entering the process. Since most products or services are created via multiple processes, you multiply the first-time yield for each process to calculate an overall first-time yield. So let's say that you prepared a dozen, 12 cookies and placed them in the oven, but 2 come out burnt and thus are inedible. We would divide the 10 by 12 to give us a first-time yield of 0.833. But let's say that a product goes through 3 different processes before the end results is achieved. You may have started with 100 products, but only 95 were good after the first process. 89 of them were still good after the second process, and 80 were good after the third process. Now, we wouldn't take that 80 and divide it by the 100. Rather, we would calculate each individual process separately, which would be 95 by 100 for a first-time yield of 0.95, 85 by 95 for a first-time yield of 0.89, and 80 by 85 for a first-time yield of 0.94. We would multiply all 3 together to give us an overall first-time yield of 0.79. The rolled throughput yield, or RTY, provides a probability that a unit will be generated by a process with no defects. One of the main differences between the rolled throughput yield and basic yield or first-time yield is that the rolled throughput yield considers whether rework was needed to generate the number of final units. This is a valuable concern because organizations don't always think about the rework that is inherent to a process, which means they often measure a process and deem it successful even if MUDA is present. Rolled throughput yield is calculated in a manner similar to first time yield, but it takes rework into account. If process A from the first time yield example only achieved a yield of 95 because someone reworked 5 items to make them good, then the rolled throughput yield calculation add 5 instances of rework into the ratio. It is calculated by subtracting the number of scrap and rework from the total number of units entering the process, then dividing that by the total number of units.